I will build the CNN architecture now, as I told. First, I have to split the data set so that I can have separated data sets for training, validation, and testing. Uh, I chose 70s to 20s to 10 proportion, and in that way, I had 75,000 samples for training, 21,000 for validation, and around 10,000 for testing set. So initially it's better to start with a simple data set. So I chose a VGG16 data set, which which is found online. So what I did was I had that data set first. I started with that architecture first, and then I was playing with its parameters and various epochs, and I was continuously checking what kind of training accuracy I'm getting. So when I saw that, I got training accuracy of around 90% for 15 epoch, and I did the validation and I got 88% accuracy. I was happy. I thought it's acceptable. So I decided on moving to the next stage, which is the testing stage, because I got consistent accuracy for training and validating. That means the model has learned well. So this is the final architecture which I came up with after lots of trials and errors on the VGG16. So the first layer, so there are in total 18 layers, and the number of total parameters are 37,000. And the first layer is zero padding. The reason why I kept zero padding is when we do convolution, the filters are slided over the input image and convolution is taken place. So in order to save the boundary or the pixels from edge, I use the zero padding, and the input image size is 224 by 224 in VGG16 model. That's why while reading the data set, I made sure that my images are getting resized in this shape so that it can easily fit into the model. And then as I told, then comes the pooling layer, and after those convolution and pooling layer, we do the flattening, and finally we use the fully connection layers. And yeah, so this is the architecture I used. So next, when I got satisfactory result in as training accuracy and validation accuracy, I chose to do the testing. As I told, I had around 10,000 samples for testing, so I just used that for testing. And I so the idea is that if there is similarity between the validation and testing accuracy, that means the model has learned well. But sometimes it happens that the training accuracy is very good but the validation accuracy is not, or maybe those accuracies are good but the testing accuracy is not. That means either the model has learned very minor details or it has learned nothing at all. So it's very important to find a consistency between the three accuracies, which is training accuracy, validation accuracy, and testing accuracy. So then I performed testing, and what I saw as results I will show in next slide. But the first result which I wanted to show is the relation between epoch and the accuracy. So every time I change the parameters, I allowed the model to be trained for multiple epochs, and I saw that with an increase of the epoch numbers the model was learning gradually. That's why there is a rise in training accuracy with the increase in epoch, and there is a rise in validation accuracy also with the increase in epoch. But after some time, when I ran it for more epochs, I saw that they almost become saturated. That means it's taking a lot of time because I'm running so many epochs, but it's not adding any accuracy to the system. That means it's just like wasting time but not doing any additional job. That's why I stopped there and I decided that I will have only 15 epochs for this system. So after testing, these are the results. So another important thing is to have at least 3 or 5 fold cross validation, because it might happen that randomly I chose some data and the accuracy results are very good, but in the long run, maybe next time when I'm doing, uh, I may not get the same results. That's why I did 5 fold cross validation. That means every time when I splitted the data into 70s to 20s to 10, I chose different samples. I did random shuffling first on the data set, and then I did the split so that I made sure in every fold I was using different data sets. Okay, so for the first set or first fold, the training accuracy is 91%, validating accuracy 89%, and testing accuracy was 89%. So see, there is a consistency between these two. And the second fold, again for second and third fold, I got 91% accuracy for training. For validating, again I got some similar accuracy, and testing accuracy was also in between 88 to 89. And finally, in the last two folds, I got around 89% accuracy, which is still good. And validating accuracy is either 87 or 86. And testing accuracy is also similar. And in order to prove that the results are statistically sound and there is very less variance, I took the standard deviation, median, and average. So we can see that the standard deviation is near 1. That means there was very less variation. The median value is also very good. That means there was very less, the result was almost consistent for training, validating, and testing accuracy. And finally, in my project report, I actually used the average value for explaining all the details. So I think these show pretty sound and consistent results, because I did 5 fold cross validation, and in all the folds I got almost similar results. So the conclusion is, this is how I can, or anybody can, easily design a CNN based architecture for face recognition. And I also demonstrated the results with FRGC dataset, which had a lot of samples, which is 106,248, and the testing accuracy achieved was 88% with the 15 epoch. And also it is very important that one should keep varying the parameters and must do the needful processing, because only doing this too, uh, it is possible to ensure a good accuracy from the CNN based systems. So this was the first part of my YouTube content. So in next part, I'm going to demonstrate some results from the computer programs I wrote in Python. Thank you, and don't forget to watch the next video.